Hello and welcome to this video about vector space proofs. This proof is about linear dependence, which is the opposite of linear independence, because there's at least one vector in the set that's the sum of the others. But this isn't part of its definition, so that it needs to be proven, and this is the proof. So now we'll look carefully at what the theorem is that we have to prove. We'll start by defining the set A to be a set of n vectors. The theorem says that this set of vectors is linearly dependent if, and this is if with two f's. It's a way of saying if and only if, because the theorem works in both directions. One of the vectors in A can be written as a linear combination of the other vectors in A. And this is another way of expressing this, that one of the vectors can be written as the sum of the other vectors in A multiplied by different constants that are scalars of these vectors. The WLG stands for without loss of generality, which means that when we use the first vector in the list, then if for some reason the first vector on this list couldn't be expressed as this sort of sum of the other vectors in A, then we could always swap this vector with another vector in the set that could be, and then call this vector the first vector in this set. So now to look at what the definition of linear dependence is. We'll define the set A to be this set of n vectors. And so we'll have to define a condition for which we can say that A is linearly dependent. So the condition is that we have to find n constants that are not all zero. That is, they aren't allowed to all be equal to zero at once. So that this sum of vectors adds up to be the zero vector. If the set was linearly independent, then we couldn't find such numbers. And this isn't the same as saying that one of the vectors is a linear combination of the other vectors in the set, which is what we have to prove. So here's an example of a linearly dependent set. We'll set these three vectors to be equal to these row vectors. And we'll set A to be the set that contains them, and we'll claim that A is linearly dependent. And this is how we'll show it, by adding up this linear combination of these three vectors to give us the zero vector, showing us that we can find these non-zero constants for which we can do this. And so now to actually evaluate this sum to show that it's the zero vector. So we'll substitute all of these vectors into this expression. Then we'll evaluate this sum of vectors, which gives us a row of zeros. And this row of zeros is the zero vector. So we've just demonstrated that these vectors are linearly dependent. So now to start the proof, we'll start it in the forwards direction given by this arrow. We'll define the set A here to be this set of n vectors. We'll suppose that one of the vectors can be written in terms of the others as a linear combination. And we'll let this vector be x1. The WLG stands for without loss of generality, which means that if the first vector in this set can't be written as a linear combination of the remaining vectors, then we could just swap the vectors about so as to get a vector that could be written as the sum of the remaining vectors, and then call this the first vector. And this is what it means for x1 to be written as a linear combination of the other vectors. It's the sum of these vectors, with each vector multiplied by its own corresponding constant. We'll call these constants C2 to Cn. It starts at C2 because the second vector is the first vector used to create this sum. So we could subtract xn from both sides to get this equation, which is equal to the zero vector. We don't need to invoke the theorems for a vector multiplied by -1 or 0 here. We'll just assume them for now. This equation happens to be a non-trivial linear combination of these vectors that happens to be equal to the zero vector. Or in other words, it's a linear combination of these vectors when not all of the constants are equal to 0. And this is the definition of linear dependence that we looked at earlier. So we've just proven that the set A is linearly dependent. So we've just completed the first half of this proof. The main trick in this proof is to manipulate the equations in the middle of this proof. So now to do the second half of this proof in the reverse direction, because the theorem says if and only if, we'll start out by saying that the vectors in A are linearly dependent. So we can write out this equation, which is the definition of A being linearly dependent. And we can assume without loss of generality that the first constant is non-zero, because we could always swap the first vector with another vector in the set that has a non-zero constant, and make that the first vector, and its corresponding constant non-zero. Then we can solve this equation for x1, since c1 is non-zero. And so this is one of the vectors being equal to the sum of a linear combination of the vectors in A, so that the constants are not all zero. And that completes the second half of the proof, and therefore the whole proof. So this proof is all about interchanging these two equivalent equations. The exact value of these constants isn't important here. What is important is that we change the form of one of these equations into the form of the other. So we could make up a sort of alternative proof with double arrows, so that after we prove the forward direction, then we can very easily go in the reverse direction, because we have the double arrows between every step. We'll turn this statement into an equation of one vector being this sort of sum of the other vectors. Then we'll manipulate the form of it to be this. We can invoke this WLG condition to move between the two equations, since we can always swap the first vector with another one in the set. And so this is the definition of linear dependence. So we've proven the first direction of this proof, and we've also proven the second direction because we've used double implication arrows. So I hope that you can see the mechanism of this proof. We can't just assume that one equation implies the other. We have to actually manipulate the equation before we can use words to describe it. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write some helpful suggestions and ideas and to share this video. And thanks a lot for watching.